Hello, my name is Caitlin Logozo, and I will be presenting the artificial blood vessels that I designed and simulated. So what I will cover today is a brief introduction as to what artificial blood vessels are and a bit of their history, the designs and simulations that I ran, along with the data that I collected in order to come to a final product recommendation based on the data that I collected and a cost analysis. So, brief introduction. Artificial blood vessels are also known as vascular prostheses or vascular grafts. They've been a breakthrough in biomedical engineering and have been rapidly generated over the past 70 years. Most of them are made out of biocompatible polymers, but now the focus has shifted to bioengineered materials, especially when it comes to creating small diameter vessels, as they seem to be much more complex. Most polymers don't have the elasticity to handle biological anomalies such as thrombosis, which makes them not perfect for the type of design that is necessary. So I decided, in order to simulate a small blood vessel design, using the knowledge and research that I have collected while bioengineered materials are still in the works, figured this would be a good simulation to run in order to see which polymers would work best in this situation, as bioengineered materials are still being tested and developed. So here are the designs that I came up with. So a small diameter blood vessel is anything under 6 millimeters. So I developed a design with a 4 millimeter diameter, inner diameter, and the outer diameter being 4.7 millimeters, allowing for 0.70 millimeters of thickness. There was 3 designs that were created: a 1 millimeter, a 10 millimeter length, and a 100 millimeter length. I tested 3 polymers, biocompatible polymers, one being polymethyl methacrylate, also known as PMMA, polyvinyl chloride, which is PVC, and polypropylene. I chose these materials since they were biocompatible, and they were also not polymers that I had seen in my research that were tested. So I figured this would be a good group of polymers to test in these simulations. First, I conducted a flow simulation. The flow simulation was conducted with the average flow rate of an average human male. That is about 5 liters per minute. This was multiplied by five times that rate, and it was converted into meters cubed per second for the specifications. I used this simulation in order to gain the pressure that would be built up within the blood vessel and get the maximum pressure. Then once I had the maximum pressure, I ran static simulations with 2 fixed ends, as the artificial vessel would be within a person if it was used. And then I tested the maximum pressure on the inner walls of the vessel in order to get the stresses and strains the vessel would experience under these conditions. From the flow simulations data, as you can see, all 9 of the samples that were tested were exposed to the same flow rate. For the 1 millimeter and the 10 millimeter designs with the different polymers, they experienced the same maximum pressure. It wasn't until I tested the 100 millimeter length vessels that there was actually a difference, mostly with the polypropylene. it yielded a 768 kilopascal maximum pressure, while PVC and PMMA ranged around 151 kilopascals. After getting all of these values for the maximum pressure, I then ran static simulations where this showed better results as to the differences that the materials would have with these conditions. For both the 1mm, 10mm, and 100mm, PVC had the lowest maximum stress that it would experience under these conditions. It's good to have the lowest maximum stress, meaning that the vessel isn't necessarily experiencing breakage, like it won't expand so much. Then based off of the cost analysis, as you can see, PMMA costs about $3,200 per metric ton. PVC comes in at $1,182 per metric ton, and polypropylene at $1,208 per metric ton. Polyvinyl chloride, being PVC, is the cheapest out of the three, and it also yielded the lowest maximum stress at all lengths. So for the final product recommendation based on the economic concern and the values observed in the simulated data, PVC would be the recommended material to use in the creation of a small diameter vascular prosthesis for the time being, while bioengineered materials are still in the works. And here are the references that I used to collect my data in order to run these simulations. And that will be all.